In this video, we will talk about the conversion of equations between polar and Cartesian planes. So let's get started. Let's start by looking at this introduction question, which states, how would you graph the polar coordinate equation r equals 6? Well, first notice that this equation is in terms of r, and we know that this is a polar coordinate equation, since for Cartesian, we usually have the variables x and y. And for polar, we have the variables r and theta. So notice that this equation is just stating, let's graph a function whose points have a value of r equals 6. But what do we mean by this? So if we go back to our graph, notice that we just want to pick points which are exactly 6 points or 6 units away from the origin. So here's my origin. Notice that every circle indicates 1 unit, so 1, 2, 3, 4, 5, 6. So notice that this point will be exactly 6 units away from the origin, so therefore it is part of this function. And also this point right here, so this is origin, so that's 1, 2, 3, 4, 5, 6. This point definitely fits the description of this function because it is 6 units away from the origin. And notice that here we have another one, 6 units. Here we have another one, 6 units. And also, in addition, this point will also be considered part of this function. So hopefully you start seeing a pattern, but pretty much every single point that will be on this circle will be in this function, will be part, or it is part of this function. So what we have actually have done is that when we try to graph a function who's only given in terms of r, all we have done is we have graphed a circle whose center is at the origin, where the radius of the circle is the value of r. So all we have done, we have graphed a circle whose center is at 0, 0, and the radius is 6 units. So this is how you might want to think about functions in terms of r. If the r is constant, which in this case the constant value is 6, we want to graph, or we want to place a collection of points which are 6 units away from the origin. And notice that all those points that we chose fits that description. So therefore, all we have done, we have graphed a circle whose center is at the origin, and its points are exactly 6 units away from the center. Now let's go into something a little more complicated now. But before we go into the actual task, which is the idea of conversion of equations, let's just review two things. Let's just review how can we go back and forward between polar and Cartesian plane. And again, recall that for polar, we have the coordinate point r theta, or the radius in the circle, and for Cartesian, we have coordinate point as x comma y. So recall that if you've been given a polar coordinate point and you want to transform them into Cartesian, remember that the x value is equivalent to r cosine of theta, and remember that the y value is r sine of theta. So given a point in r comma theta, to transform them into x comma y, we use these transformation functions. Now, if we've been given a point in Cartesian and we want to transform them into polar equation, well, notice that we have two conversions. First, to get the value of theta, remember that we have this. Oops, I'm sorry, it's y over x. To get the value of theta, we can use this equation. And to get the value of r, recall that r squared will always be equal to x squared plus y squared. And this is something that we discussed in our previous lesson, but I just wanted to refresh you. Another thing that I would like to discuss is, before we go and start transforming functions, recall that for Cartesian, most of the time, the standard form, it's always in this format, y equals some expression. Now, for polar equations, the standard form will be written in terms of r. On the Cartesian, the standard form is mostly always written in terms of y equals some expression. But now we want to write down equations in polar form. Our standard form will be in terms of r. So we're going to have r equals some expression. So now that we have refreshed all this and we have just discussed these 2 quick points here, let's actually go into the actual task, which is the idea of converting. Is it possible for us to go between Cartesian and polar? Yeah. Well, let's start by doing that. Let's convert the following equation, which is given in rectangular form, and let's convert it into polar form. Therefore, our equation should only be written in terms of r and theta. So let's get started. Let's start by looking at how the equation is written. It says y equals x squared. Therefore, we want to get rid of the y and the x and just write it in terms of r and theta. But I know that the x value is equivalent to r cosine. And I know that the y value is equivalent to r sine. So let me just plug that in. So instead of y, I'm going to write it as r sine of theta. And instead of x, I'm going to write it as r cosine of theta. And notice that now this equation, it definitely has the format that we needed because there is no x and there is no y. So everything's in terms of r and theta. So now our objective is to properly write it in standard form, in the form of r equals some expression. So how do we do that? Well, first notice that the right-hand side still has an exponent of 2. So let's just simplify that. Let's just expand that. So you got an expression all to the second. Remember that r is multiplying cosine. So this is equivalent to r squared times cosine squared. And now notice that I want to write it all in terms of r. So therefore, it will be a good idea for us to divide both sides by r. By doing that, this r cancels out, and now this r cancels out the second exponent. And what we have left is the expression sine of theta equals r cosine square of theta. Again, we just want to write in terms of r, so we're going to divide both sides by cosine square. And now we have an expression r equals sine of theta over cosine of theta. And now notice that this is exactly what we wanted. We have a function who's in terms of r, and the only variables present in this function is r and theta. But this expression, we can still simplify it, even though this is okay. This is okay to be our final result. We can still simplify this, or at least we can write it differently. Notice that we could have simplified, or we could have rewritten this way. So instead of cosine, I'm going to write cosine times 1 over cosine. Notice that we have not changed anything. Still sine at the top. Cosine times cosine is cosine squared. And now this would give us the expression sine over cosine. This is equivalent to tangent. And 1 over cosine, this is equivalent to secant. It doesn't really matter if you write it this way or this way. They mean the same, since they both have the requirements that are needed. It is in terms of r, and the only variables that are present is r and theta. And now, how do we know that we have arrived to the same conclusion? Well, let's just graph them and see if it gives us the same result. So here we have our equation y equals x squared, which is just a very nice parabola. But now, if we change our grid to polar coordinates, sorry, and now if we graph the equation that we got as a result, notice that we have exactly the same equation. It is exactly the same curvature. The only difference is that one is written in terms of Cartesian and the other one is written in terms of r and theta, which is polar coordinates. So all we have done, we have represented the same equation, but now in terms of r and theta. Let's continue. Let's take a look at a couple more examples now. So now we want to still do the same task, which is here is an equation written in Cartesian, and we want to write it in polar form. Let's do the same approach. X, let's write it in terms of its polar representation, which is our cosine. Y, let's write it in terms of its representation in polar. And 9, well, 9 is 9, so there's nothing to change there. Okay, so let's simplify this. R cosine to the second, that's equivalent to just r square cosine square to be a plus. We got r square sine square, that's equivalent to 9. And again, we want to rewrite everything in terms of r, or we want to isolate the r. So notice that here we can factor out an r square. So we have r square, and now we have cosine square plus sine square is equal to 9. But notice that here we have a trigonometric expression, identity. Cosine square plus sine square, this is equivalent to 1. So therefore, we could just rewrite it as r squared times 1 equals 9. We can still simplify this, and now we have r squared equals 9. And even though now we have r by itself, we have it to the second exponent. So therefore, we need to get rid of that exponent. So we divide by r. And now we have that r is equivalent to plus or minus 3. But now we have to be careful here, because now, which one do we choose? Do we choose r to be positive 3 or r equals negative 3? Well, r represents the distance from the origin, and distance is always positive. Therefore, r is equivalent to just 3. Notice that this was the long way. This was definitely the long way. Uh, what was the short way? Well, if we go back to the same problem, x squared plus y squared equals 9, we'll notice that this is exactly the representation that we have here. Because we know that x squared plus y squared is equals to r squared. So we could have just substituted r squared right away here. And now we would end up with the same r squared equals plus minus 3, where r is equals to 3. And notice that this kind of makes sense. Because now, if we take a look at the original function that we were given, x squared plus y squared equals 9, you can see that this is a circle with the radius equivalent to 3. And that's exactly what we got in our polar coordinate representation, because r equals 3. This is just a set of points who are 3 units away from the origin. Just like we did on the introduction question. So now r equals 6, it was just a circle with the radius of 6. In our example, we have r equals 3, which is a circle whose radius is 3, which it fits the equation that we were given originally. Let's do a couple more examples where we do the other way. So now, here we have polar coordinate equation, and now we want to write it in terms of Cartesian, so just variables of x and y. So how do we go about that? Well, if we have a sign, if you have an expression that is expressed to be sine, notice that it kind of fits here. Because I know that sine, I can convert it into a y. But it's not just sine. We need to have r times sine. So it's like here we're missing an r. If we would have an r here, then we could have just substitute r sine with the y. So how can we fit an r here? Well, notice that here we have 4 times sine. So perhaps if we multiply r to both sides, r squared on the left, now we have 4r sine. And now notice that this is essentially the expression that we need to substitute with the y value, because r sine is y. So now I know that the right hand side can be written as 4y, since r sine is equivalent to y. But not, we still gotta get rid of this r business, because if we want to write it in terms of rectangular equation or Cartesian form, we don't need an r, we just need x's and y. But notice that r squared, that's equivalent to x squared plus y squared. So we're going back to our problem. R squared is equivalent to x squared plus y squared. And I notice that this is exactly what we needed, because now we have an equation. We definitely have an equation who doesn't use the value of r and theta. So to make it just an equation, let's just move the 4y to the right hand side, and then we would have been done here. So now if we would have graphed this equation, that would have given us the same format as our equivalent for sine. Actually, before we go into task number 4, let's actually verify our results. So here, let's see if we actually have the same equation. So let's graph the function r equals 4 sine of theta. So here we have our function 4 sine of theta. And now let's see if it actually have the same equation if we would have graphed the function as x squared plus y squared minus 4y equal to 0. So here, notice that our first equation is in terms of polar form. So now, if we change this to Cartesian, x and y, notice that our result matches up. So therefore, our conclusion is true. The equation for sine is equivalent to this big expression. So let's just do one more example here. Take a look at task number 4. And again, we want to write everything in terms of x's and y. So the first thing that I notice is that I almost have the same problem here as we did in task number 3. I have a cosine, but I kind of need r cosine for me to just substitute it with an x. So I'm missing an r. So how can we go about this? Well, we cannot just multiply r on the bottom. But what I can do is notice that here we have a fraction equals to another fraction. So therefore, I can cross multiply now. And if I cross multiply, I'm going to have r times 1 minus 2 cosine equals 3 times 1. And if I distribute this r, so now that becomes r minus 2r cosine of theta equals 3. And I notice that now we have the expression that we needed. Here we have r cosine, which I know that that's equivalent to x. So now I have r minus 2x equals 3. So we're almost done. The only thing that we need to get rid of, in some sense, is the value of r. But if we take a look at the expressions that we had initially, we only had an expression for r squared. And we need an expression just for r. But since this expression is 2, since r squared equals x squared plus y squared, then it is also true to say that r is equivalent to the square root of x plus the square root of x squared plus y squared. So therefore, we can go back to our problem and now substitute the value for r. So now, r, that's equivalent to the square root of x squared plus y squared minus 2x equals 3. So notice that here we have a y, one variable that is in terms of y, so we can definitely solve for it. So how can we solve for y? Because we want to write it in standard form. So now we have x squared plus y squared. So if I add 2x on both sides, now I have the expression 3 plus 2x. Again, we want to try to solve for y. So to solve for y, we raise both sides to the second exponent. That way this cancels out. And now we have that x squared plus y squared equals. If we expand this, we're going to get the expression 4x squared plus 12x plus 9. And again, we're solving for y, so therefore I need to get rid of this x squared. That way this cancels out. So now I have that y squared equals, well, if I combine like terms, notice that here we're just going to have 3x squared. And if we want to solve for y, we need to take the square root. So now, therefore, I have my equation. Plus or minus the square root of 3x squared plus 12x plus 9. So now we know that the original equation, r equals 3 over 1 minus 2 cosine theta, it's equivalent to just graphing this equation right here. Now let's see if our conclusions were true. Let's graph the function r equals 3 over 1 minus 2 cosine of theta, and let's see if it matches the same curvature as our result. So here we have our function that was given to us. So here it seems to be a hyperbola that is opening left and right. So now, okay, so I think one thing to realize is that notice that this hyperbola, it's in terms of r and theta, so therefore it is in polar coordinates, so this will be the right representation of it. So now if we want to graph the same function, let's see if our result gives us the same curvature. So here we're going to have the same expression that we have here, but now I'm using first the plus. So plus and our result. Notice that here my exponent I'm writing as 1/2, because that's how you can also rewrite fractions. Roots. So notice that this is the plus of our result. And now if I add the minus of our result, notice that I complete the same curvature that was given to us by the original function given in polar coordinate form. So notice that our result is true. This function that was given to us in polar coordinates can be represented in Cartesian by these two functions. The plus square root of this expression and the minus square root of this expression.